Calculus BC, we are looking at accumulation functions, jumping into them a little bit further. Great problems that are going to be on your Chapter 5 test and will no doubt likely be on your AP exam as well. In some way, they'll definitely be there, whether it's multiple choice or free response. They could show up quite a bit, because they connect derivatives and integrals, a very important idea. But look, we've got g of x is equal to this integral from 0 to x of f of t dt. This right here, of course, is what we'd call our dummy variable. And, we're using that dummy variable because if we had everything with an x, then inside of the integral, we'd have to have that being the same numerical value. So look, I'd like for us to, just see that f is the function that is graphed down below here. And we're going to jump in and just take a look. By the way, this is from section 5.3. Once you've gotten through 5.5, honestly, you're just in review mode. You're truly just going over older material and diving in a little bit more deeply. By the way, we've done some of these problems as well in the video of 5.3, if you look back on it. But in any event, they want you to find g of 0. G of 0, my goodness, if you had g of x is equal to the integral from 0 to x of f of t dt, well then, of course, g of 0 would just be the integral from 0 to 0 of f of t dt. And guys, that's always just going to equal 0. The integral from 0 to 0, no matter what you're integrating from, it's like saying find the net area from 0 to 0. Area is two-dimensional, and that's all you have. So you'd say, wow, okay, g of 0 is 0. Well, what else? We could say g of 1. Now, g of 1 would be the net area, 0 to 1 of f of t dt. And this is where we're going to come to our graph here. And you know what? I'm going to embolden this a little, really make it jump out a little bit more. Hopefully, really just letting you see, the outline of this graph. So, as you're looking at that, you could say, well, I want to find the integral from 0 to 1. Well, you know what? They're saying find the net area from 0 to 1. And dare I say, sorry, my computer's having a little bit of a delay. From 0 to 1, guys, that would be from here to here. And very quickly, you could say, well, my goodness, that is simply going to be the area of that rectangle. Base of 1, a height of 2. So without too much work, you're going to be able to see that this is just equal to 2. It's a rectangle, with a base of 1, height of 2, right? Well, wow, now we've got that one worked out. Well, you could say, well, then they want you to find g of 2. Well, g of 2 is going to go from 0 to 2, isn't it? And, as you're working this thing out, you could say, well, from 0 to 2, wow, as we just come up this way, obviously we still have our, answer from before in yellow, but I'm going to draw in maybe over here in blue. You could see we've got this, and you'd say, well, wow, how about that? Well, geometrically speaking, you could see that really going from 0 to 2, if you wanted to, you could look at this as a big square right here, a 2 by 2 square with a triangle squeezed in there. How about that? Wow. So, you could say with a square of 2 by 2, of course, that's going to be an area of 4. And then up here with this triangle, you could say, well, that triangle has a base of 1, that's from 1 to 2, and a height that's, now here we've got to be careful, this is 2, 3, 4. You can see your height's actually going up 2 steps. So the area of a triangle is base, 1/2 base times height, if you'd like. And very quickly, you could see that that's just going to be a 1. So we'd get the area of that big square right here. We just found that to be a 4. Right here, that's a 1. So that's going to actually just be 4 plus 1, which is a 5. Right? So you can see they want us to keep going here and see where this all is going to go. And that's all well and good. And these values that we're having, no doubt about it, they're going to come into play later. You know, you don't always have to find so many on a typical College Board problem, but let's just keep going. I think it's just some good practice. G of 3, well, we're going to integrate from 0 to 3. We're going to say, how about that net area? Guys, here's a great property of integrals. This is from 0 to 2 plus then from 2 to 3. You know, we could look at it that way. And we talked about that before. It's almost like that barrel of monkeys theorem that we talked about. And you could say, well, wow, it's the answer you just came up with. It's all the area we just came up with there. We saw that was 5. But then you could say, well, what about from 2 to 3? Well, from 2 to 3 is another triangle. Look at that. That's another triangle. And from 2 to 3, you'd have a base of 1. But look where we're going. It's all the way up here at, what is that? That's 4. So we're going to very quickly be able to work out a 1/2 base times height. And you could see that's actually going to be a 2, right? So that area of the triangle there is a 2. That means the integral from 2 to 3, because it's above the x-axis, you know, that's going to be positive area. 5 plus 2 is 7. Hey, look at that. G of 3 is equal to 7. Well, my goodness, we still are going to have to come back and, you know, address, you know, what G of 6 is. Now, G of 6, as I'm going to just come over this way and, you know, just say from G of 6, obviously that's the integral from 0 to 6 of f of t dt. You could see that what we just found, and now I'm going to erase, you know, on the inside, we just found that the area up to the 3, and I'm going to highlight that in blue, the area that we have here, we just said was 7, right? We worked it all out. But now we're trying to also go all the way up to 6. Now 6 is up here, and dare I say, I'm going to highlight this in red. You can see that this thing right here, and I'm going to highlight it, is a trapezoid. See, that's a trapezoid. So, you know, again, what I want you to see is really this G of 6 was the integral from 0 to 3. But then we're going to also add to that, and you know what, I'm running out of some space here. Then we're going to go from 3 to 6, right? We're going to go from 3 to 6. So tell you what, I'm going to erase this part right here. You know, since we've already done that, just buy ourselves a little bit more space. But G of 6 is going to be the integral, like we just said, from 0 to 3, and then from 3 to 6. So we found that 0 to 3 was 7. We're totally good with that. But what about from 3 to 6? In yellow, that's a trapezoid. It's from 3 to 6. You can count the bars here. You can see you got a base of 3. Right here you have a base of 1. That's a height of 2. And why am I bringing that up? The area of a trapezoid is equal to 1/2 base 1 plus base 2 times your height. Well, I now know that my base would be 3 up at the top. You know, that's from 3 to 6. You could also subtract. Down below, I've got a base of 1, and my height is a 2. And the 2 and the 1/2 are going to cancel. 3 plus 1 is going to be a 4. But guys, it's below the x-axis, so that's going to be an area of -4, just from the integral from 3 to 6. Where are we going with this then? Well, plain and simple. Plain and simple. 7 plus -4 is just a 3. So we have a bunch of function values. We've got a bunch of points that we could plot on our curve. We really could, go ahead and make actually a pretty good curve here. And you don't typically have to do that a lot in the College Board's test. Even on my test, I'm not going to ask you to do a ton of areas like this. We're just really, getting a lot of good practice right here, and I hope that's going to help you out. But let's move on to part B on what interval is G increasing, and then where does G have a maximum value? And they're going to imply perhaps just in general that it's a local max. If we can definitely say it's an absolute, we can talk about it. But let's just see if we could real quickly, well, here, I'll bring that back. Let's just say that down below for B, we're interested in where G is increasing. G is increasing where G prime of X is positive, right? We know that. G is increasing where G prime of X is positive. So what you want to do is revisit this problem. We know that G of X is equal to the integral from 0 to x of f of t dt. And guys, as we saw from earlier, the fundamental theorem of calculus part 1, G prime of X, remember the most general form that we have is to plug X in here, the upper bound, multiply by the derivative of that upper bound, which is just a 1. Then we plug in, we say minus, plugging in our lower bound of 0. The derivative of 0 is 0. And this is the most general way to deal with the derivative of a accumulation function. When you just have an x up here, it's pretty easy. Kids will just say, oh, the derivative of g prime of x, it's just f of x, right? So that's super, super, super important. So I'm going to say g prime of x is f of x. But I'm interested where f of x then is positive. Where is f of x, which is graphed up here? Now I'm going to erase just to clean it up just a little bit. And you know what? I think I might just embolden the curve again in red just to make it stand out. But the big question is, when is f going to be positive? Well, f is positive when it's above the x-axis. And right now you could say very quickly, here's a 1, 2, this is a 3. You could say, wow, from 0 to 3, g prime is positive. So they're saying on what interval is that going to be increasing? We can say g is increasing. Remember, with increasing intervals, we want to use closed intervals. We always use brackets there. And that's where f is positive. Okay? For part C, they're saying, where does g have a maximum value? And by the way, I know they didn't ask this, but if you were to look at where g is negative, that's over here, isn't it? What you could do real quickly if you wanted to, you could say g is decreasing on the interval from 3 all the way up to 7, right? And right there, that might give you a huge, huge hint about how to proceed with part C. You know, with part C, they're saying, where does G have a maximum value? Well, you know, we could revisit the first derivative test. You know, here's G, and we know that G prime of x was equal to f of x. We know that from what we had just seen previously. And G prime is 0 at x equals 3 and x equals 7. Right? You'd say, well, how do you know that? Well, f is equal, and I'm going to make a big red dot right here. F is equal to 0 right here and also right here. And you could see it's those two locations where f is 0, but that means G prime is 0. So look, we can real quickly then do the following number line test. We could say, hey, here's a 3, here's a 7. Up from 0 to 3, G prime f was positive. That meant G was increasing. We just said that. From 3 to 7, G prime was negative. That means G was decreasing. You can see that we've got a local max at x equals 3, because G prime changes from positive to negative. Okay? So that's very, very helpful. That's very helpful right there. Now I know that my function G, local max G has a local max at x equals 3 because G prime changes from positive to negative. So my goodness, as we're looking at this, we now have all these points from part A. I know when G is going up, when G is going down. I know that I actually am going to have a local max. From the context of this question, you can actually say it's going to be the absolute max on this interval. You can see that this function never is going to rise up again. So you could actually call it the absolute max and be 100% correct. But there's one additional part that I'm going to get into before we make a rough graph here. Making a rough graph, I'm sure kids will say, oh my gosh, look at all these points that you have. Yeah, we've got a whole bunch of them. I also know where I'm going to have a local max. I also know where I'm going up, I'm going down. Maybe the one thing that we haven't talked about, maybe the one thing that we haven't discussed is actually very pertinent. Maybe we could say, what about an inflection point? Do we have an inflection point or inflection points here? And I know that's not even part of this assignment that you're seeing right here on this problem, but it will be asked for sure. It will be asked for sure. So, hey, listen, I've done some work here for the sake of space. I'm going to real quickly just erase this stuff just so that we could pull together some additional information. We know, and I'm going to call this for, we could call it C part 2, if you'd like. We could say find inflection points, if any. Find inflection points, if any. Well, we need to talk about the second derivative. Look, g of x, we already said, was from 0 to x of f of t dt. That means g prime of x is going to be, when you take the derivative and it's just an x, the shortcut is to say it's just f of x. And then what? G double prime of x is equal to f prime of x. So if I'm going to look at where g double prime is 0 or where g double prime is undefined, wow, that gets to be kind of interesting, doesn't it? I can look at f prime as the tangent line slopes. So, wow, this is crazy, guys. This is really something. I can really get a lot of information right now. Check this out. The tangent line slope is 0 here at that first step. You'd say, oh my gosh, would you look at that? Look at this. This is crazy. I could say G double prime equals 0 on a whole interval from 0 to 1. Wow. Where else? Between 5 and 6. That's where it's completely flat. It's completely flat. But G double prime, pardon me, G double prime of x equals 0, I meant to say. G double prime of x doesn't exist at corners. So that's at x equals 1, x equals 2, x equals 3, x equals 5, x equals 6. Holy smoke. There are plentiful places where, because of corners, G double prime, which is f prime, wouldn't exist. So let's just see if we can real quickly get an idea as to what is happening here. I know that, we've got numbers like 1, 2, 3. So I'm going to say over here is a 1, here's a 2, here's a 3. We're going to keep going. Over here's a 5, here's a 6, and, then over here's 7, and here's 0. So G double prime, now watch this. Yeah, it's 0 here, and I'll just put O's there instead of a plus or a minus. Those are zeros, right? Same thing right here if you want to. It's just a reminder that G double prime is 0 there, not just at one place, but a whole bunch of places. Holy smoke. At 1, it doesn't exist. At 2, it doesn't exist. At 3 and 5 and 7, wow. And at 6, I should say. But look, I guess what I want to point out to you is between 1 and 2, this tangent line slope is positive. So that's definitely positive. Between 2 and 3, M is negative. Look, that's a negative tangent line slope. Between 3 and 5, look at that. M is negative. And finally, between 6 and 7, that's positive. So right now, I know that G is linear between 0 and 1. Between 1 and 2, it's concave up. Between 2 and 3, it's concave down. Between 3 and 5, it's concave down. Between 5 and 6, there's no curvature. It's a line. And between 6 and 7, it's concave up. Wow. Wow, do we have a lot of information right here. Is there an inflection point? Does concavity change? And the answer to that is yes, and that's at 2. So there's an inflection point. Now, you already did some work in part A, and that's at 2, 5. From part A, you found G of 2 is equal to 5. And find inflection points of G of x, we should say. We should always distinguish that. So G of x has an inflection point at 2, 5 because why? G changes from concave up to concave down. Nowhere else. So, wow, we are really, really diving in here, and no doubt we are truly getting into a lot of information. So, guys, real quickly, I'd like for us to make that rough sketch. This is really a problem that is just packed full of so much. Look, from part A, you have so much. Right now, we're going to graph g of x. G of 0 is 0. That's saying that you've got the point 0, 0. That's right here. You have g of 1 equals 2. That means you've got the point 1, comma 2. G of 2 was equal to 5. And sometimes we're going to make a much rougher sketch here. G of 3 was up here at 7. And G of 6, let's see, we could say here's a 3, 4, 5, 6. G of 6 is going to be over here at 3. So, hey, I've got a whole bunch of points here. I really do have a lot of information. But look, this is what I really want to talk about. Usually kids will say, well, of course, we know that, G was increasing from 0 to 3. G is decreasing from 3 to 7. And you have a maximum at x equals 3. In fact, your maximum value is 7. And usually kids will look at that and they'll say, hey, that's exactly what we would have come up with if we would have just plotted these points. Well, the calculus gives you a surety that that is actually the case. But look at this now. I can say from 0 to 1, I'm linear. From 0 to 1, this connection is actually a straight line. Okay? From 1 to 2, I'm going to be concave up like a cup. Right? Then from 2 to 3, I'm concave down like a frown. Now, of course, we're going to have a corner point. We know that G prime of 3, actually, as you're looking at that right there, well, pardon me, I said that we'd have a corner point. Sorry, I was looking at the graph of the derivative. You can see that this graph of the derivative, as we're the derivative of f, that has a corner point. Does that mean that there's a corner point at x equals 3? Well, no. I think you can see just from this context, we knew that g prime of 3 was 0. And I think that's something that kids definitely need to talk about. G prime of 3, which was equal to f of 3, that was equal to 0 just because, right here, f, which is the derivative of g, has a corner right here. That doesn't mean that we've got a corner over this way. I just want to be very, very, clear about that. Sometimes kids feel like there must be a corner up here. No, the calculus is telling us it's not. We're going to be concave down until we get to 5. And then it's going to be linear. It's going to be linear from 5 to 6, right? And then we're going to go concave up like a cup, but it's going to continue to go down. They didn't ask us to find where that was, but it's going to be concave up like a cup. Of course, we could find it, but notice what is coming into play, guys. The fact that there are linear parts, the fact that that second derivative, had those steps, between 0 and 1 and 5 and 6. That's where that was completely flat. So definitely wanted to point that out to you. Hopefully that's making sense. We're going to keep diving into this, and hope you guys are having a great break. Tail end here, we got to get ready for our last test. Hope all is going well.